The joke about fusion here on Earth is that it's been 20 years away for the past 60 to 80 years. And so the question is whether we can ever bridge that gap. The conditions that are required to ignite a fusion reaction are extraordinarily hard to produce outside of the context of the center of a star, where you have just massive gravitational forces. You need a machine, you need some sort of system that produces a state that is hot enough and dense enough for long enough.
All right, folks, just 20 seconds of context before we start. This is part 2 of the mini-series with Andy Lubershane, partner at Energy Impact Partners, one of the top funds globally in the energy market. In the first part, we talked about nuclear fission, which is a reaction that's already powering a country like France, for example, with a lot of nuclear reactors. In the second part today, we're talking about something that's a bit more difficult to understand, which is nuclear fusion, where we basically have invested billions and billions of dollars into trying to maintain a fusion reaction long enough so that it provides energy to civilizations. And we're not there yet, but it feels like there's a lot of progress happening. So I thought that was a good conversation to have with Andy Lubershane. Enough about me talking. Here is Andy Lubershane to talk about nuclear fusion.
Fusion here on Earth, what we hope to achieve, is fusing two lighter atoms together. And actually, fusion, the merging of two atoms into one, is even more of a highly energy generating reaction than fission. And I think, as most people listening to the podcast know, fusion is probably the most abundant source of energy in the universe, powering the stars. Again, is this big global technological challenge that the joke about fusion here on Earth is that it's been 20 years away for the past 60 to 80 years. And so the question is whether we can ever bridge that gap.
Yeah, and I think in your newsletter, an article, you said it will be ready when we need fusion. And I think, it's difficult to argue against the need for abundant and clean energy today. So I guess that leads me to kind of, the next section of this, which is, why is it so difficult? Because it feels like we need it right now. So if that person, which I can't recall the name, was right and it will be available when we need it, why isn't it available today?
Yeah, that was a quote from Lev Artsimovich, who was a Russian scientist and is known as the quote, father of the tokamak, tokamaks being one approach to potentially harnessing fusion energy terrestrially. Said that fusion will be ready then when society needs it. Society probably needs something like it now, right? And so question is whether he was right. Fusion, the reason fusion is so incredibly difficult from a technical standpoint is that the conditions that are required to ignite a fusion reaction, to start a fusion reaction, are extraordinarily hard to produce outside of the context of the center of a star, where you have just massive gravitational forces that are providing all of the energy that's necessary to get the reaction started. And by the way, I should preface all of this by saying that I am not a physicist. I've learned enough to be a little bit more than dangerous over time, but I hope that any physicists listening to this give me some grace, as I'll probably get 1 to 5 things wrong. But I'll do my best here, which is that physicists, fusion scientists talk about this phenomenon they call the triple product, basically, which is the product of 3 variables that are required to create a fusion reaction that can potentially produce more energy than you put into the reaction to get it started. And that triple product is, the variables are the density of the reaction. You need to get the atoms that you want to fuse very, very close together, closer than they would ever come to each other in ambient natural conditions. The second variable is temperature. So the atoms need to be in a very, very highly energetic state. So you need to get them extremely hot. And then the third variable is that those two first conditions need to be maintained for a long enough period of time such that you get enough fusion reactions to, again, produce more energy than you put into the machine in order to generate that high density, high temperature condition. So, again, fusion scientists will often say you need a machine, you need some sort of system that produces a state that is hot enough and dense enough for long enough. That's the triple product. And just to give you a sense of why, again, like that's so challenging, when we say hot enough, we're not talking about any kind of temperatures that are sensible, that are really comprehensible to the human mind, right? There's a couple of different versions of fusion reactions that are out there based on different types of fusion fuel that we might use. But the lowest temperature we're talking about is about 100 million degrees Celsius. And so, wildly, hotter than anything that would ever be created here on Earth. And the ideal fusion reactions we might be able to achieve, which use much more abundant fuel, are over 1 billion degrees. So again, like just, incomprehensible for our brains. And it's in the form of a plasma because that's the state of matter that anything that hot will be in. And we're trying to squeeze that plasma into, a dense enough condition to fuse the fuel inside. And this is where my lack of physics knowledge, I'll do my best to explain why that's even harder than it sounds. But among physicists, plasma is kind of notorious as a state of matter for being extremely hard to deal with. It's not like a liquid that stays within the four walls that you put it in. And so, for the purposes of commercial fusion, like plasmas don't like to be contained. The way that I've heard this described, the metaphor I've heard used is that trying to contain a plasma, trying to squeeze it and make it denser is like trying to squeeze grape jelly in the palm of your hand. Like it just wants to slip out through the cracks between your fingers. Any little mistake is going to release the plasma. And this is actually an advantage of fusion over fission in some ways. The advantage of fusion is that these conditions are so hard to produce and maintain that there's basically no risk of a runaway fusion reaction. Unlike, a runaway fission reaction that could cause a nuclear meltdown in a fission energy facility. In the case of fusion, as soon as you turn the thing off, like as soon as you stop trying to make it ridiculously hot and dense, the reaction stops. And so there's no risk of a runaway, explosion in that kind of sense. The challenge, of course, is that those conditions are just wickedly, wildly hard to produce.
And I can imagine that in order to get it to such level of temperatures, you need to put a lot of energy into the reactor in the first place. I'm curious, like I was reading through a few articles before this episode, and some articles mentioned that we've been able to achieve this Q above 1, so this ability to basically produce more energy than it's required to start the reactor. But is that accurate? Does that account for everything? Or where do we stand? Have we achieved already on Earth something that produces more energy than it needs to get going?
Yeah, so just to emphasize that, the North Star for fusion research has always been this state that they call Q equals 1, which basically is the ratio of energy that comes out of the reaction to the energy that you put in. So if Q is below 1, it means that you're putting more energy in than you get out. If Q is above 1, it means that you've successfully made energy, net positive energy from fusion. There was a headline a few years ago from a facility called the National Ignition Facility, which is a fusion research facility at Lawrence Livermore Lab here in the US, that they had achieved a milestone which was interpreted in many cases by the media as Q equals 1. And narrowly speaking, you could say that Q equals 1 was achieved at this facility. And what this facility was using is an approach to fusion called inertial fusion. So essentially what they were doing is firing high-powered lasers from many directions at sort of surrounding this fuel at the center of the facility. And in doing so, compressing the fuel and heating it up at the same time to try to, for a brief moment, but again, for a long enough moment, create the conditions for Q to achieve Q equals 1. And so if you draw sort of a system boundary around that fuel, the energy from the lasers that hit the fuel, it's true, was less than the amount of energy from the fusion reaction that the fuel produced. About two megajoules of energy came in from the lasers, and that produced about over 3 megajoules of fusion energy. So that's impressive. That is a scientific milestone that is important and should be recognized. But I think it was a little bit over interpreted by the media, because what actually happened at the National Ignition Facility is these lasers that were used to power the reaction are extremely inefficient. One of the problems of the kind of laser, the technical challenges and gaps in fusion we have today is we don't have the efficiency and cost of lasers that would make this really successful. So it actually took about 300 megajoules of energy to power the lasers that ended up producing this reaction. And so if you draw the system boundaries around the full human machine that we produced, then it took way more energy to create this fusion reaction than we put in still. So I would consider this an interesting and important scientific milestone, but not like a relevant commercial or engineering milestone for fusion as an energy resource.
And we'll get to it in a minute, but there are some announcements from companies like Commonwealth Fusion that says that next year they will start producing energy with a smaller size kind of fusion reactor. We'll get to there in a minute, but some people on Earth that are much more expert than I am on this technology think it will happen very soon as next year.
I actually am one of those people. I mainly because I believe credible researchers and teams at companies out there that I believe it's very likely in the next few years that there could very well be multiple fusion efforts that achieve that Q equals 1 milestone honestly, as in like the total amount of energy they spend is less than the total amount of energy they produce. Commonwealth being, one of the leading contenders that's out there. Commonwealth, I'm actually feel really lucky. I know a few people there, and I'm going to get to go there later this month and check out the spark reactor that they're building in Massachusetts. So as an energy nerd and just someone who likes cool giant machines, regardless of the prospects for fusion, I think it's going to be really fun.
You have to send me some pictures if they allow.
I'm not sure I'm allowed to, but I can describe it. Yeah.
What you've described so far seems like an incredible, difficult task at hand. What makes you think that this is still worth pursuing? What are the if we compare it to fission, for example, why are we pursuing fusion if it's so hard to do?
Yeah, I mean, the prize for fusion, I would say there's kind of 3 reasons to prefer fusion over fission, some of which are stronger than others, if we could achieve it cost effectively. First, as we talked about in the last episode, the fuel for fission is very limited in supply, and it's pretty geographically concentrated where we can mine uranium out of the ground cost effectively, where we can enrich it. The supply chain is risky because there's nuclear weaponry, proliferation risk, etc. Whereas the fuel for fusion is basically widely available all around the world. There's kind of 2 fusion reactions that are primarily being considered by companies that are developing fusion technology. One is called DT, or deuterium tritium. The other is called proton boron, or PB11. And proton boron basically is that's the harder fusion reaction to achieve. That's the one that requires billion degrees temperatures, and there's actually many fewer companies that are pursuing PB11 fusion. Most fusion is focused on deuterium tritium, but proton boron, the fuel for that, which is essentially hydrogen and boron, which is available in seawater, is basically infinite. Like that is a truly infinite energy resource here on Earth when it comes to human use. Deuterium tritium is trickier because tritium is not available in nature, in rarely extraordinarily scarce in nature at the kind of concentrations that we would care about. It's an isotope of lithium, and lithium itself is not an extraordinarily abundant resource. And so we would need to significantly step up our production of lithium if we were going to really rely on deuterium tritium as a fuel for fusion reactions, at global civilizationally relevant scale over time. And we don't have to get into it now, but the way that you'd actually probably produce tritium in that scenario is that you would breed it from the fusion reaction itself, because when you bombard lithium with radiation, with neutrons that would come out of the deuterium tritium reaction, it converts that lithium into tritium. So like the actual fusion reactor is probably also going to be producing its own fuel, which is also like a crazy difficult engineering challenge, by the way. Less difficult than creating, 100 million degrees for long enough period of time and containing a plasma, but one that, layers on top and makes this even more technically challenging. But the short story is like, we believe that fusion fuel is probably easier to come by in the long run and more scalable than fission. I think that's less of an advantage for fusion. The second advantage I mentioned is that I already mentioned is that fusion has no real like meltdown or runaway reaction risk like fission. So you just don't have to be concerned about safety in the same way, which has implications for the cost of a facility in terms of security and protective barriers and the amount of land that you need to be cleared around the facility. And then third, fusion reactions, deuterium tritium, the more common reaction we're pursuing, does still produce radiation, harmful radiation, but it produces much less and at a much lower level of radiation and radioactive waste than fission reactions. It's the kind of waste that you'd sort of like, it's been classified similarly to the radioactive waste that's produced from radiation in a medical facility context, as opposed to a nuclear fission power plant. And so, the dream of fusion is basically the same as fission. Imagine if you had nuclear fission, this like extremely power dense, effectively infinite energy resource, as long as we keep looking for more fuel over time, just without any of the downsides of fission in terms of safety, proliferation risk, or long-lived harmful radiation. So it's kind of like, if you get it right, again, it is in many ways like a perfect energy resource.
If fusion ever happens, which you believe it will, how much of the world's needs of electricity and power could we achieve through fusion? Like, what's the size of the reward if all of that happens?
I think that to answer that question, I need to clarify what the meaning of if fusion happens. And I think this is really the key point here. Because like I said, I am bullish on science and engineering capabilities of some of these extremely well-funded companies that are out there. At Energy Impact Partners, we've invested in one fusion effort, a company called Zap Energy, which has a very different approach than Commonwealth and the father of the tokamak that I described at the top of the show. And I think that they and some others will get there. The challenge with fusion is that, can they get there cost effectively? I mean, that really is the big question, because of the extraordinary technical difficulties of making this happen, the high materials requirements, the fact that you're going to have a completely new fuel supply chain, particularly for deuterium tritium, which is the more likely fusion reaction that we're going to get commercially in the short term. It's very possible that we will get these big scientific breakthroughs. Like we'll get to Q equals 1, we'll get to Q equals 10, but it costs $500 a megawatt hour and nobody wants to buy it. Like that is a plausible outcome. Actually, the reason that we, picked Zap as our horse in the fusion race, so far at EIP is we think that if they're able to achieve the scientific milestone, they have one of the best shots at actually building a cost-effective, affordable system out of that. But I think that currently, my best guess is that there's the scientific milestones come much sooner than the commercially relevant milestones for fusion. But if we're able to do it, to kind of in the spirit of your question, if we could get to this cost-effective fusion reactor, and let's say we get lucky and it's proton boron fusion, so we can find all the fuel we'll ever need, then I don't know, that basically solves humanity's energy supply problems, right? Our primary energy problem. It doesn't solve our energy carrier problems. We talked about in the last episode that fossil fuel is both a source of energy and an energy carrier. But it goes a long way. So in that sense, fusion is a fusion level bet if we're able to make it happen.
Makes a lot of sense. Well, look, we will still have to score it on the scorecard. Let's do that in the next couple of minutes. Okay, well, the elephant in the room. Let's start with cost. You have to give a grade from 0 to 10 on cost and affordability of fusion.
I'll say we'll give it a midpoint of 3 out of 10, maybe 2 or 3. I don't want to go down to 1, and I'm hopeful we can do better, but there's so much uncertainty there.
Yeah, it's. I'm sorry for that very tough question. Security and safety for humanity.
10.
No risk, basically. Okay.
It's the least risky, least impactful.
CO2 emissions also 10.
Also 10.
Okay, speed of deployment.
Well, it depends how fast we're able to invent and commercialize this stuff. But once we do, theoretically you can pump these things out. So let's go with a 5 there, and I'm optimistic that we can actually make the technology work commercially.
Nice. And then last one is scalability.
Also, again, if we get the best version of fusion, proton boron fuel, then it's certainly a 10. Even deuterium tritium is probably a 7 or an 8.
So last question for you, is it worth betting on fusion in the long term?
In the last episode, we talked about how much I'm a bull for nuclear fission energy, and that I really believe that it's probably the biggest bet that society, from a societal benefit standpoint, we should be putting much more into deploying fission energy today. But I do think it's worth society investing in fusion as a long-term energy resource. And it's an important bet we should be making, even though I don't think it quite deserves the place among fusion level bets that it has captured in the public imagination.
We'll have to do a summary at the end of the series of ranking all of the technologies. But look, fantastic episode again. In the next episode, we are diving deep into crazy cheap renewables, because when solar gets cheap enough, it doesn't just power homes, but it also starts powering entirely new industries. If you like this series, please don't forget to like, comment, and subscribe if you're on YouTube, or to follow us on Apple Podcasts and Spotify. Don't forget also to subscribe to the newsletter at the link in the description, and to end this newsletter as well, which is really fantastic, one of the best out there, much better than mine for sure. And send this to your friends that still think that fusion is the only way out of the energy crisis. Thank you so much, Andy.
Thanks, Hugo. Great to be with you.